we need to talk about how do these labels get assigned? How did, for example, R1 know that it needs to use label 53? How did R2 know that it needs to use label 71? And so on. Now, to explore that, we are going to talk about the MPLS control plane. Now, when we talk about MPLS control plane, inevitably we have to talk about different MPLS databases that are in use. And I'm going to say MPLS under quotes here because some of these databases are not actually directly tied to MPLS. Some of these databases are used for regular IP forwarding as well. So the databases that we actually care about when we talk about MPLS are RIB, or also known routing table, we have FIB, which is the forwarding information base, and in most cases these days in Cisco routers this is CEF. Then we have something called LIB, which is label information base. And we have something that is called LFIB, which is the label forwarding information base. Now, let's take a look at how these databases are built. Now, before I do that, I'm just going to give you a quick cheat sheet here because you know that I really, really like cheat sheets. So I'm just going to turn this into a very, very quick table. And let's see here. So here we are going to have database. And let's add here a field that is going to be the lookup command. So let's see which command you can use in Cisco iOS to actually look into the information of this base. Now, for routing table, which is, let's just, let me rename it quickly here. It is the routing table, but the proper name for it is routing information base. So this is our routing table. So the information, the command to look up the information in the RIB is, of course, show IP route. Now, to look at the information in the FIB, if we are dealing with CEF as the FIB, which is most likely the case, is going to be show IP CEF. To take a look at the label information base, we can have multiple commands because unfortunately in Cisco iOS you can have multiple tables. So let me write this. These could be multiple tables, and I'll explain that a little bit later on. So one of the commands you can use is show MPLS LDP bindings, or you can use, for example, show, not shop, but show IP BGP labels. And this is if you are using BGP for route. So let me put this here. But this is the one that you will most likely use. This is if you are using LDP or TDP in your network. Now, to look up the LFIB, again, you can have multiple commands for that. One is show MPLS forwarding table. Which will show you LDP and TDP derived labels. But it may not show you those labels that have been perhaps installed in the routing table by other protocols that can exchange labels, and we'll see what protocols they are. So if you want to see the full table, you can actually do show IP CEF. Now, the reason why you can use show IP ceph here is that fib and lfib in iOS are actually parts of the same database. So this is basically, in both cases, ceph table. So fib and lfib in iOS are, technically speaking, subsets of the same table. So let's see how these different tables actually interact with each other. So let's say that on our router we have a routing table. So here we have the routing table. Now, a routing table is populated with the information from routing protocol. So different routing sources actually feed our routing information base. Now, based on the route information base, what is going to be created is going to be our forwarding information base, or our ceph table is going to be populated. So information that is going to be feeding fib is actually going to be information from the RIB, but also it's going to be information from layer 2, layer 3 mappings, like for example ARP tables, frame relay maps, etc. So this is the information that is actually going to be fed into the fib and in the RIB to actually make up our forwarding information base. Now, the information in the label information base, so this is our lib table here, is going to be comprised on information based from the routing table and also from label exchange protocols. Now, these label exchange protocols are, for example, LDP, TDP, BGP, RSVP, or static labels. So all these feed information into the label information base, and this information then in combination with the data coming from lib, RIB, and fib actually feeds the information into our lfib. And both lfib and fib are really subset. Let me try to be good with this. Really straight horizontal lines are not my thing. There we go. So this is really one database in iOS. So this is the relationship between the different databases in iOS. But let's see how they are actually built. To do that, I'm going to go to pretty much this same example. So I'm going to have the 4 routers, R1, R2, R3, R4, and I'm going to have 2 hosts, A and B, here, that are going to try to communicate. And again, I want to send the traffic from A to B, which means that my label information needs to flow from B back to R1 and A there. So let's build that network. So I'm going to redraw it here. So we have R1, R2, R3, and then R4. So let's say that this is going to be host A, this is going to be host B, and again, this is the edge of my MPLS network. And what I'm interested in is traffic going this direction. So this is the traffic. Actually, let me do that slightly differently, like this. So this is where the traffic will be going. And that means that information needs to flow in the opposite direction. So let's say that this is R1, this is R2, this is R3, and this is R4. Now, before I proceed with this example, I should point out that in order to get an operational and functional MPLS network, what you need to have is a fully operational and fully functional IP network. If your IP network doesn't work, your MPLS will not work. So this example assumes that you actually have a fully functional and fully operational IP network. So whatever routing protocol you are using here, you are fine. Now, one thing that I should point out, and for this, the emphasis comes in. Contrary to popular belief, you do not have to run OSPF or ISIS to run MPLS. MPLS will run with any protocol in the backbone. You can run it with RIP, you can run it with EIGRP, you can run it with OSPF, you can run it with ISIS. Any protocol that you like, you can use. Now, the only protocol that MPLS really doesn't like is the protocol that people usually associate it most with, and that is BGP. If your network is 100% BGP, and as I mentioned when I talked about BGP, BGP really cannot replace your IGPs. If your only protocol in the network is BGP, your MPLS may have some problem with it, not necessarily problem, but the approach to your building of MPLS infrastructure in that case needs to be different. Now, MPLS works fine with BGP, but it actually needs an IGP to operate properly, at least with iOS. So with that emphasis done, let's go back to our example. So you can run any protocol, including static routes here. But so which protocol we are running is irrelevant as long as we all agree that these routers actually have the knowledge of the route. So the only route that I care about is actually the route for B. So let's say that in my example here, the black color, so I'm going to put it here, is going to contain the information or represent the information in the routing table. So let's say that R4 here has in its own routing table, in its RIB, has information that B is directly connected route. R3 here has the information that B is reachable through R4. And by the way, let me just add the interfaces. So 0, 1, 0, 1, 0, 1, 0, 1. So here we have in our routing table the information that B is reachable through R4, and let's say that it's reachable through interface 1. Here we have information that B is reachable through R3 out of interface 1, and here we have information that B is reachable through R2 via interface number 1. So this is the information in the routing table. Now, obviously, whatever the actual layer 2 here is it Ethernet, is it frame relay, is it serial connections, is it carrier pigeons, whatever it is, we have some layer 2 to layer 3 resolution protocol. So based on that information, we're going to know what the remote side is, and given that information and information from the RIB, so we are taking the information from the RIB and from these layer 2 resolution protocols, we are now going to build the forwarding information base. So blue information here is going to be the forwarding information base. So here we have information that B is reachable. So let me just create a copy of this page, just one sec, so that you can have actually incremental examples when you look at this later on. So just going to delete this here, and we are going to have it on the next page. So let's say here that we have the information that B is directly connected out of interface 1 and whatever the layer 2 information was. Now, here we are going to have information that B is reachable out of is reachable through R4, 1, and whatever the layer 2 information was. Here we are going to have the information that B is reachable through R3 out of interface 1, whatever the layer 2 information is, and here B reachable to R2 out of interface 1, whatever the layer 2 information is. Now, at this point, let's bring in the red color. Now, the red is going to represent here our label information base. Now, before I go with this example, let me first talk about two protocols that are extremely important for MPLS. They are LDP and TDP. These are both label exchange protocols. Now, I am deliberately avoiding to use their names here because I want you to kind of remember what is it they do and not necessarily their names. LDP stands for Label Distribution Protocol. and TDP stands for Tag Distribution Protocol. Now, tag here is the old name that Cisco used for MPLS. Cisco used to call it tag switching because Cisco actually invented it. Now, when tag switching became popular, sometimes in early to mid 2000s, other vendors started, getting on the bandwagon. And what happened is that IETF did what IETF does best. They took Cisco's white papers, did a bunch of search and replace operations, and replaced all occurrences of tag with label and all occurrences of tag distribution protocol with label distribution protocol. But other than that, other than this being Cisco proprietary, operation of these two is almost identical. In the iOS, they share the same databases, they exchange information in pretty much the same way, except that they use different port numbers. So they cannot talk to each other, but they operate in the same way. So the port numbers that are used by LDP are 646 UDP, and 646 TCP, and ports in use by TDP are 711 UDP and 711 TCP. Now, all other operations are almost identical other than this one supports authentication, and there is no authentication supported by TDP. And also, TDP is unlikely on the exam. Now, when I say that something is unlikely on the exam, this is what I believe is the case. Now, when I believe something is the case, but they actually mention it on the blueprint, like they do actually mention it on the blueprint, I actually have to mention it myself. Now, I find it very, very unlikely to be on the exam, so this is it. This is the only thing that I'm going to say about TDP, but I've already said enough. LDP and TDP operate in almost identical manner. This is how they operate. So, I'm going to take a look at the example of LDP. So let's say that we have two routers. So there is R1 here, and let's say that there is R2. And in this case, we actually fired up LDP. So we configured LDP here, and we configured LDP here. How do you do that? You go to Interface, X, and you say MPLS IP. This by default will actually turn on LDP on this interface here. We did the same thing here. And what happened is LDP actually started working. So when LDP starts working, so let's just now observe what happens in this direction here. What's going to happen, the first thing is from an interface address, there will be a hello sent. Source is going to be interface IP, and destination is going to be 224.0.0.2, or all routers multicast address. Now, this router here also sends back the hellos. So the source here is the interface IP, and destination is 224.0.0.2. Now, once they know about each other, and just like with any other hello, it works in, hey, these are my parameters, and this is the list of routers that I see. Now, when I see the hello from other neighbor, I'm going to include his hello, his MPLS LDP ID in that message. I'm going to say, hello, my name is R1, these are my parameters, and I see R2. Now, when R2 sees its own ID in an interface, we know about each other. Now, one thing that happens next is extremely important for R2. Unlike OSPF, the LDP ID is an actual IP address. So in OSPF, we know that router identifier, or in BGP for that matter, is just a number that looks like an IP address. But here it is an actual IP address. And this address must be reachable because of what happens next. What happens next is there's going to be a TCP session between these two. And this TCP session is deterministic. Let's say that that loopback address here was 2222 and here it was 1111. It will be R2 that initiates this TCP session towards R1. Why? Because this number here is the higher number. So it will always be the higher number that initiates the TCP session towards the lower number. So this here will be the TCP session. Now, the port number used here is going to be 646, and this is going to be UDP. The port number that was used here is 646, and this is again UDP. The port number that is going to be used here, so the source IP address will be LDP ID, and the port number is going to be random. And destination here is going to be LDP identifier, and the port number is going to be 646 TCP. So this here is a TCP session that gets initiated. Now, the reason why we have this TCP session and why we are not exchanging information inline here is that these two routers could have multiple links between them. And if they have multiple links, they might have multiple links that are actually sending hellos. But because they will be exchanging the exact same information about their databases, there is no need to exchange this information multiple times. This is why we are going to build the session between the loopbacks, which is going to be the default for LDP. So LDP by default will be the highest, will be the loopback with the highest IP address. This is why we have this TCP session between the loopbacks. So going back to our example here, so let me create a copy of this page. So going back to our example, let's say that we enable LDP on all of these devices. So I have turned on LDP, so let me just mark it here. So LDP is on here, LDP is on here, LDP is on here. Let's start from R1. So when you turn on LDP on one interface, let's say that we have not turned it on R2 just yet. What R1 is going to do is it's going to go through its routing table, and based on its routing table, it's going to build the local lib. It's going to say, okay, I have route B. This is the local label. And the local label is going to be just some number. By default in iOS, the pool starts from 17. Actually, 16 is the last reserved one. So it starts from 17, so the first label that you will get will be 17, or maybe it's 16, but around that number. You can control that with the command is mpls label pool and label range, and then you can specify the range of labels that you want to actually use for labels. But let's say that R1 assigned label 100. Okay. Now R2, when you turn on the LDP on at least one of the interfaces, it's going to do the same thing. So it's going to assign the local label. Let's say that 3 does the same thing. And B here says, oh, this is the local label, but you know what? I'm going to be using implicit null. So it assigns an implicit null. Okay? Now, let's say that LDP has been established between R1 and R2. iOS uses something that is called unsolicited exchange of labels with liberal retention. In plain English, this is what it means. LDP is now established, and now R1 and R2 are going to send each other the contents of their locally assigned labels. So whatever labels they have locally assigned, without the other router actually asking for them, they are going to be sent out. This is what the unsolicited part is. So R2 is going to tell R1, hey, if you want to reach B, you can reach it through me. So this is going to be the label from R2. Use label 200. So this is the information that we actually learned in this direction. But the same thing is going to happen in the other direction. R1 is going to tell R2 that if it wants to reach B, it can do that through R1 with label 100. So this information came from here. Now, if we take a look at our diagram, this is a complete nonsense, because there is no way that R2 can actually reach B through R1, because B is in this direction here. But you know what? R2 is actually going to keep this information in its database. This is the liberal retention part. It's going to keep even the information in the table that it doesn't actually need. Now, the same thing is going to happen in this direction here, between 2 and 3. So we have the label exchange here. So now R2 is going to learn that B is actually reachable through R3 using label 300. So this information came from here. Now R2 is going to tell R3, hey, if you want to reach B, you can do it through R2 with the label of 200. Keep in mind that only local information is sent. So this information is sent here. Now R4 and R3 establish their connection, and here we get the information that B is reachable through R4 using the implicit null. So this is the information we actually learned from here. Now R3 tells R4 that nonsense information that B is reachable through R3 using the label 300. So this is the information that came from here. So this is the information that we have in the lib. Now if we go back a couple of pages in our whiteboard, now we have to build the LFIB, and the information in LFIB comes from the lib, comes from the rib, and from the fib. So we have to now compile this information into something that MPLS can use. So this is going to be, in our diagram here, information displayed in green. So this here is going to be LFIB. So we're going to take the information from the rib, we're going to take information from our fib, and we are going to use the information here that we have. So we are going to build the entry that B can be reached through R2 out of interface 1 with label 200 using the following layer 2 parameters. Now, there is going to be one more entry that's going to be built. Entry built based on this label. Now, technically speaking, in iOS, when you are looking at the LFIB, you are going to see this all on one line, but I think it might be easier to understand if I show you these two entries separately. The second entry, apologies for that, the second entry that is going to get built is that if you receive the packet labeled with 100, send it to R2 out of interface 1 using label 200 with the following layer 2 parameters. Basically, we are telling it, if we receive this label, this is where we need to send it out. Now, let's see what R2 does. Now, R2 does, here it says that B is reachable through R3, so we are looking at this, is reachable through R3 with the label, out of interface 1, with the label 300, with the following layer 2 parameters. But again, we need to look at the local label. What happens if we receive the traffic with the local label? So if you receive traffic labeled 200, do the exact same thing. Same thing here. We are going to say that B is reachable through R4 out of interface 1 with label nothing. The implicit null means do the pop. So let's say, well, there is actually not going to be pop label, it's going to be nothing there. Implicit null will be visible here, so this is why we have no label. And use the following layer 2 parameters. Also, if you receive the traffic labeled with 300, send it to R4 out of interface 1 with no label with the following layer 2 parameters. In R4, there will be no LFIB entry for this network. Why is there no LFIB? Because this here is unlabeled traffic. This here is the IP traffic. So this is how MPLS databases actually get built. So now, let's see what happens with the traffic. let's say that the packet arrives. So let me draw a nice packet here. Let's say that the packet now arrives from A that is supposed to go to B. What's going to happen here? A is going to see, oh, what's the destination? It's B. Okay, I do have the label for it. So what does the LFIB say? It says send it to R2, okay, and label it with 200. Okay, so we are going to install the label 200. Now, this same packet arrives to R2. So what do we have to do here? We are saying, oh, this was the packet that was sent with label 200. So I'm not even looking at these here. I know this is a labeled packet. What does it need to do? It needs to go to R3, out of interface 1 with label 300, remove one label, add another label. So the label 300 gets installed here, and then the packet goes on. What happens on R3? On R3, what happens? Oh, we received the packet with 300. It needs to go to R4 without the label. Bam, sending the packet. What happens on B? We are receiving an IP packet. It's directly connected. It needs to be sent to B with the following parameters. So this is how the packet actually gets sent. Towards our destination. So this is how MPLS forwarding actually works, and how the label exchange in MPLS works, how the databases are built, and how that information is actually exchanged in the MPLS network.